We're continuing in section 6.2 in the subject of phase. Phase is a relative term to compare two or more sine waves that have the same frequency. Sine waves that are in phase have various identical points occurring at exactly the same time. The terms leading and lagging are used to describe the relative position of sine waves with respect to each other. In image A, two different alternators are generating a signal. Note that the loops are shifted 1/4 turn or 90 degrees. This accounts for the 90-degree phase shift. And so if we look over here, we can see that here we have the two alternators, and you'll notice that this one is at this particular cross-section where it's cutting maximum magnetic flux lines, and this one is in parallel with the north and the south pole. Now this one is actually shifted 1/4 turn, which equates to 90 degrees. And so if we look at it on this scale here, the black dots here are going to equate to the black phase signal here, and this is at the 90-degree point, which is right here. The blue one, this equates to 0 degrees, which is going to be, and in parentheses we see the 0 degrees, which is right here. And so we see that these are shifted 90 degrees. Now, remember, the mention here was made of leading and lagging, and this would be the leading sine wave, and this would be called the lagging sine wave because it is lagging in time. Remember, when we, if this was a, let's pretend that this is our 60 hertz signal, and remember that the time of the 60 hertz signal, we said it was what, 16.66 milliseconds. And if that is the case, then we can look at the time from here to here as well. And so that is 1/4 of the signal, and that's going to be about 4.167 milliseconds. So this signal starts, and then 4.167 milliseconds later we have this signal starting. And so this would be the leading and this would be the lagging. And in this particular case, the reason that it's lagging is because the generator that is generating the signal is 90 degrees out of phase with the leading signal. And let's see, down here I have a picture. This is not from your text. This is showing three-phase industrial power, and if you've ever come across that, well, the three phases are actually 90 degrees apart. Okay, phase angles are measured in degrees or radians. Make sure your calculator is set up for degrees. For this particular course, we will be dealing with degrees. We will refer to radians, but most of our calculations will be done in degrees. So let's look at your calculator, and calculators will come in many sizes and shapes. Under options here, notice we have something here for angle. And so we need to make sure that we are set for degrees. This would be in radians. If you were calculating angles and you have this set for radians, you're going to get the wrong answer. So make sure that you're set up to measure degrees. Okay. And we'll say OK there. So our calculator now is set up to measure in degrees, and we can move on here. Okay, instantaneous values. We can express the voltage or current at any instant during a sine wave's cycle. The instantaneous voltage of a sine wave is 0 at 0 degrees. And instantaneous voltages and currents are found by using this formula. And the instantaneous voltage could be found by taking Vp times the sine of the angle, and wherever we are in the angle based on the degrees. And to illustrate this, let's draw a sine wave. Let's see if I can draw a kind of half-decent sine wave. That's not too bad. And so here we would have 0 degrees. This would be 90. This would be 180. This would be 270. And this would be 360. And so what this is saying is that we can calculate the voltage at any point in this signal. So let's give ourselves a value. Let's say that this signal is, the amplitude is 10 volts peak. But we want to know what is the signal going to be at, say, for example, let's say at 45 degrees right here. We'll calculate it there. And let's have another one at, say, 70 degrees. And let's have one down here also. Let's say we'll have it 210. And let's take a look at those. So with our calculator, let's bring up our calculator, and let's input some values here. Let's start out with 45 degrees. So we're going to say 45, and I'll click on sine and take that times, notice times the peak value, which is 10 volts, and we'll say equals here. And so what we just calculated was the instantaneous value. What is in this particular sine wave at 45 degrees, what is the voltage? And it is 7.07 volts at 45 degrees. We could likewise calculate it for 70. So let's go in and say 70 sine times our peak value of 10, and that's very close to our peak of 10 at 70 degrees. We're at 9.39. And let's just confirm that this actually works. Let's say at 90 degrees. So if we went 90 sine times 10, and that would yield our 10 volt peak signal. Likewise, let's confirm at 180. So let's say at 180, the sine value is 0, so times 10 is going to be 0. So that's 0 there. And then let's go to 210. So if we went 210 sine times our 10 volt value, and notice it is minus 5 volts, and that's what it should be, because we're looking at a negative voltage now. We're on the negative portion of the sine wave. At 270, if we went 270 sine times 10, that's where we would see our peak value, our negative peak at 10. And finally, if we did 360 sine, you notice it's 0, so that's going to be 10 again. So this is how we would calculate instantaneous values on a given sine wave. Okay, time and frequency domains. All signals can be viewed from either of two perspectives, either the time domain or the frequency domain. Fourier developed mathematical principles that link together time and frequency domains. Now, we will not be doing Fourier analysis in this particular course, but it is a subject for advanced topics in courses that would follow. A time domain signal is one whose instantaneous voltages change over time. And an oscilloscope displays signals in the time domain, and we've been talking about this. When we look at a signal on an oscilloscope, we look at it in relation to how long is this sine wave in relationship to time. Any given waveform can be shown to be composed of one or more sinusoidal signals at specific frequencies and phases, and that is the frequency, or the frequency domain. A spectrum analyzer displays the frequency domain. Now notice, any given waveform can be shown to be composed of one or more sinusoidal signals. Now if you have purely a pure waveform, sinusoidal, you won't see many harmonics. You begin to see harmonics when you deal with non-sinusoidal signals like a square wave. Any repetitive, and this gets into the subject of harmonics, any repetitive non-sinusoidal waveform can be shown to be composed of a fundamental frequency and some combination of harmonic frequencies. And so notice it is non-sinusoidal. If you have a pure sine wave, as I mentioned, you won't see those harmonics, but when you see square wave, they will be quite obvious. The fundamental frequency is the basic frequency of the waveform as determined by its period. Harmonic frequencies are exact multiples of the original frequency, and they can be odd or even. And from your text, you have a few images that depict this. Here in this particular screen, we see the blue wave here. This is the fundamental frequency. Let's just pretend that is 10 kHz. And then we have the third harmonic. Notice this signal here. This in black here. Here we have 1 cycle. We have 2 cycles, and here we have 3 cycles. So if this original was 10 kHz, then the third harmonic would be at 30 kHz. The fifth harmonic, let's look at it. Here we have 1, we have 2, we have 3, we have 4, and we have 5 cycles in the time of the fundamental, so that would be at 50 kHz if the fundamental is at 10 kHz. Okay. Here we have slide B. Now this shows the algebraic sum of the fundamental third and fifth harmonic, and in this case it's beginning to look like a square wave. Here we're looking at just the individual frequencies that make up a square wave. Here we're seeing how they would actually display if you only had the fundamental, the third, and the fifth. This is adding in the seventh, and then here we've added in the 9th and 11th, and you see that it's beginning to take on the shape of a square wave. It will not be a square wave, okay, until you have all of the harmonics, which would be kind of infinite, and then it would take on and it would look kind of like this. Okay, I have a simulation of a spectrum analyzer that we'll be looking at shortly, and it will aid in seeing how is it that you actually can view the harmonics. This is a demo using Electronics Workbench of a device called a spectrum analyzer, and in your text there was mention made of the time domain and the frequency domain. The time domain is viewed with a device called an oscilloscope, and the frequency domain is viewed with a device called a spectrum analyzer. Spectrum analyzers are very precise pieces of equipment, and they can be extremely expensive. The entry-level prices on these are probably around $3,000 to $5,000, and you can easily spend upwards of $100,000 on a really high-end spectrum analyzer. For purposes of our course, we won't be needing one of these, but I did want to demo its operation just because a brief mention of it was made in your textbook. The reference in your book had to do with harmonics, and here I have a circuit set up, and this is a function generator, and we're generating a square wave at 10 kilohertz, and the amplitude is 10 volts peak to peak, and that signal is put across this resistor right here. And the spectrum analyzer is set up across this resistor, and we're looking at the output that the spectrum analyzer displays, and I have this set up. It doesn't instantly display. I had to go in and set all this stuff up. I'm not going to go into that because we're not going to be doing that, but I did want to show you the final outcome. Now, what you see here is the fundamental frequency, and that's going to be the largest peak here, and then all of these others are the harmonics. And if I scroll over here, we can actually look at what frequency is that, and we can lock in on it fairly closely. Okay, there is 9.9, so that would be our fundamental of 10 kHz. And if we scroll over to the next one, it should be about the third hum. Okay, that's very close to 30 kHz, which would represent the third. And then over a little further to, this should be 50, about, yeah, there we are, about 50 kHz would be the fifth. and then here to almost 70, that would be the 7th. 90, that would be the 9th, and then about 110, that would be the 11th, and let's see, what's the next one here, 130, 13, anyway, so on and so forth. You get the idea here, and this would go on indefinitely. We're graphing out to 242 kHz. And like I said, there's just the limitations of how much I can display. If I put this up really high, then these get so crunched together that you can't, it's hard to decipher what's what. But anyway, this has to do, we're just wanted to display the ability to look at the fundamental and all of the harmonics. And by the way, I don't believe the spectrum analyzer is available in your student or your textbook version of Workbench. I believe you have to get at least the student upgrade to be able to use it. So I don't think you have access to this, but not to worry, we won't be using this. This is simply a show and tell item. Okay, in this lesson we looked at phase relationships. We looked at what does leading and lagging mean, and we looked at this particular waveform here. We saw that the black waveform is leading the blue waveform by 90 degrees. And we looked at our calculators to make sure they were set up for degrees. We calculated instantaneous values using the sine function on a calculator. And we discussed time and frequency domains. We will be primarily dealing with the time domain. Frequency domain is very interesting. We'll just mention it. It is a subject for advanced courses. And we looked at the subject of harmonics, and we looked at the spectrum analyzer output to better understand harmonics.